All right, so let's see, let's get started. So for deep NLP topics, the main things that I want to hit today are going to talk about like different kinds of clustering, and that's we're going to talk about k-means again, as well as that versus LDA. I'm going to talk. I know I did talk before about word embeddings, but I'm going to go through that once more so we have this recorded as well. And then at the end, a little bit about predictive text, because that could be something that definitely as like a final, like cool thing to add, predictive text. All right, so to get started, I think the easiest way for at least me to explain is to just talk about like, at least for this clustering stuff, is just talk about in context of my own projects. So I'll start with that. Let's see. So, oh, it is recording. So for context, again, if we don't know, this is a project that I've been working on. It's one of my like freelance projects, and we're basically clustering users based on what they search for on this app. And so what we're doing here, what I ended up doing a clustering. So this is the most basic clustering with like, I think you're not using any like deep NLP. So here, all I do is I have a count vectorizer. I think I literally just started by, yeah, I think I just did this clustering just using the count vectorized version. I didn't even use TF-IDF. And so what this means is that I'm literally just clustering these search terms based on their tokens. And the way that does, some pros and cons. The pros is like, it's easy to do. We already know our count vectorizer. It just gives us a table of like how many times each word turns up. But cons, like you're missing a lot of other information that could be useful, especially when we're looking at natural language. So like words that mean similar things, like maybe, let's see, supermarket versus convenience store, you would think are very similar, but with this model, they're not going to see that those are similar words. So even though we might like based on contextual knowledge, we want to group these things together with something that's just using a count vectorizer and also TF-IDF, because TF-IDF is just looking at the inverse document frequency of words. You're not going to get a lot out of context. Especially if you have like shorter. So what also comes into play now is also like your body of text. Like each of your rows, are they long or are they shorter? In this case, I have only like search terms, so they're much shorter, and therefore like you have a very, very sparse matrix. You're rarely going to see numbers above like 5. So therefore, this model didn't really work too well. So as I think I've showed you guys this before, I think I did this cluster I did 20 clusters, and it ended up extremely imbalanced. And I guess I can talk a little bit about like I guess the philosophy of clustering here is oftentimes you're going to get clusters like this. You're not going to have like 5,000 rows and have them nicely clustered into 5 groups of 1,000. Just based on where points are mathematically and the more dimensions you have. So here I have, let's see how many columns, 6,000 dimensions. You're going to see results that look very much like this. And so with this information, you see we have like literally all of these clusters have less than 10 rows in them. Several things you can do, take them out because they're outliers. Look into them and see if you can merge clusters. So let's say maybe like these last 5 clusters, after looking into what words are in each cluster, maybe I'd say that, okay, they're very similar to cluster 2. I can literally just like map out that clusters 6, 14, 7, 11, and 17 will be part of cluster 2 as well. So you have a lot of freedom, a lot of like, it gets a little manual, and this is really where you get into like the art of the data science is you get to make these decisions on your own. And so that's just pretty straightforward, clustering by the count vectorized by the tokens. And so things you would tune are like the number of clusters. So that aside, going one level up from that, if you want to introduce context, And that's really important to think about. I think for most of your projects that would use NLP, context is important. Sometimes it isn't, but context is very important when I'm looking at, like, if I want to group users together based on what they're searching or what they're writing about. So a level up from that is you use jensen to create word embeddings. So I guess to start, let's see, how should I start this part? To explain what a word embedding is, a word embedding is literally just representing a word by numbers. And when you're using different kinds of word embeddings, it can be different numbers in different dimensions. So how you introduce context, the most common way to do word embeddings is by using word to vec. And so word to vec is great because it literally means word to a vector. There are several ways you can use it. One, you can train one on your own. And I think I mentioned this in like a few study groups ago. But how you would train a word to vec model to just like recognize your corpus. So let's say you had like, let's say you had like a novel on, like, I don't know, Moby Dick is the first one that came to mind. And you want to teach a model what the word whale means. Moby Dick's a whale, right? I think. If you want to teach Moby Dick, if you want to train a model to understand what the word whale means, how it does that is it looks at the words before and after the word whale and sort of like learns based on the information around the word whale what a whale could mean. So you do that by sort of like, you sort of tell it how wide you want your window to be. So typically you would have like a word, you look like 5 words behind and 5 words forward and use that to sort of build your context of what the word could mean. And it's really very inferential. So you can do that. If you have like a very specific corpus, that's something you could do, but it takes forever to train because you're really looking and learning for every single word, you're trying to learn the context. So you're just looking at this window of words around every single word. So more commonly, what we would use Word2Vec for is by using their built-in models. And so I'm going to show you this example where I use ConceptNet, but before that, let me show you all the different models that they have. I think it's in here. So there's this jensen module that you're going to be using if you want to do word embeddings. And you would have this jensen downloader as API. I think I have, let's see, yeah, I have the documentation here and I'll send this out as well. But anyways, there are a bunch of different pre-trained networks that you can use. So as mentioned before, actually, no, I can show you exactly what these are. So this was just a notebook that I was using to explore everything that was available. So here I have a bunch of different corpuses or a bunch of different pre-trained networks. So for your project, you would look at these and decide. So a good one to look at is, I'm using ConceptNet, and ConceptNet is, let me see, oh, it's here. So ConceptNet is here. And there's like a little description saying it, state-of-the-art semantic vectors, word embeddings. And it combines data from ConceptNet, Word2Vec, Glove, Open Subtitles. Another very popular one is actually Glove, because Glove is trained on Twitter. So there's a bunch of different ones. There's Glove Twitter 100, 200, 25, 50. So these numbers actually determine how long each word vector is. So you think about, like, okay, if I had Twitter 25, if each word is represented by 25 numbers versus each word being represented by 200 numbers, you get like different levels of granularity, right? Like if each word can be represented as 200 different numbers, you can get a lot more specific, I guess. So for example, like if you had 2 words that were extremely close in meaning, maybe only like 5 out of the 200 words would be off. 5 out of the 200 numbers in the vector would be different. Whereas for like 25 words, if you only have like 25 words available, you get a little less specific with differences between words. So I can send some version of this code out to you all so you can like also explore what's available. So let's see. So what you would do is you would just load the model. And this takes a very long time to load. I think every time I download ConceptNet, it takes roughly 10 plus almost 20 minutes because it is downloading all the vectors. That's literally what they're doing. For every word that's in their corpus, they're downloading the vector. So that's why it takes a long time. Let's see. I think this is a good thing to go through. I'm not going to run the code because the outputs are here already because I don't want to load the model. What's cool is they actually have different languages at least for ConceptNet. I haven't really played around with the others too much, but the thing is, you'll see what I'm printing here is I'm looking for the words that are most similar to, let's see. Yeah, words that are most similar to coffee. This one, we'll take words that are most similar to coffee. And then you'll see that we don't only have like words, but we also have phrases, which is pretty cool. There's gourmet coffee, Starbucks coffee, brewed coffee. And I think depending on what model you use, you might have to introduce a prefix. So something that I can sort of show is I have the same example here. If you're using ConceptNet or any of the pre-trained networks and you see this error, please load. Yeah, you'll see that it's not in the vocabulary. And usually if it's like a typical word that you know has to exist there, I would look up the documentation of the specific library. It's pretty easy to find. And you'll be able to find that. It's pretty cool here. You see with coffee, you have served hot, which is surprisingly the top result. But I think these are just coffee in different languages, which is very interesting. But yeah, so that's how you would start off by like using ConceptNet, just seeing like what words exist in their corpus. And then what I have here, how would you turn something into a vector? Let's see, I have code somewhere else. See, is it in this one? This one. My files are very messy. I'm still working on it. But you can turn things into vectors. So if you look up ConceptNet sort of works like a dictionary. So I'm just gonna copy this little part because this is what I was doing. Let's say I want to look up what the vector for coffee is. Oops, you want it as a string. You can see here we have an array of length 300 because I used the 300 length pre-trained network. Length of 300 is just 300 numbers. So this is the numeric representation of coffee. So what you would do if you want to implement Jensen in your projects, you would just get all these vectors, and for each search phrase or review, or for each like row, you would just add these vectors together to create like a document vector. That's a little, yeah, that's kind of hard to explain, but like basically vectors are kind of additive. So let's say I had coffee and I also had, let's see, let's make another one and do like coffee and store. So store is another vector of 300. Because of the way vectors work, it's kind of hard to explain without going very mathy. But the way vectors work, if you want a vector that is talking about both coffee and store, you would just add them together. So you can sort of represent an entire phrase as a vector by doing this plus this. And that is and this output here is a representation of coffee store. I don't know if this will be super helpful, but this is the code that I wrote for mine. First, this is just me pre-processing like a string of text into a search vector, where basically I look for the word and see if it exists in ConceptNet. And if it does, append it to basically have a list of these 300 arrays. And then what's cool is I just sum them all together to get the entire search vector. I'll send some version of this out as well later, maybe tomorrow, because I need to like take out all the sensitive information. But yeah, so that can also be helpful when you're doing your clustering, because this now takes into consideration the context of what you're talking about. So that's what makes Jensen very powerful, is that it really takes into consideration context. There is another library out there, but I've never used it. It's called Doc2Vec, and it turns entire documents, and by documents I mean like if you have like a long string of text, it turns that automatically into a vector. I actually think it does the same thing as what I'm doing here by like just summing each word vector. I'm gonna look for the documentation, check that, and then send it to you guys if it makes sense to use. But that's about Jensen. I'm gonna backtrack a little and talk about LDA. Let's see, I think this is the one that I was sending people. Yeah, this is I think I really like this Medium article talking about LDA. LDA is different from k-means slightly. I honestly haven't looked into the math of LDA to see if it does the clustering similarly or differently than k-means. But the main difference about LDA and k-means is that k-means will assign each row to one single cluster, where LDA actually like sort of looks at all of your rows, your entire data set, and sort of assigns like main topics to everything. And then let's say, I think I have a good example here actually. Oh, it's not in this article, but it comes up with like overall topics that come up in your full corpus, and then they assign parts of your rows to each topic. So that means that each row can be assigned to different topics, if that makes sense. So the topics are basically like your clusters, and basically each row will have like some sort of probability of belonging to each cluster. So that could be more helpful because, sometimes for clustering, because you just have to make a decision as to like which cluster it belongs to. Whereas now you can say like, okay, if it's a bad review, maybe it's talking about it's an app that keeps crashing, but also it has like other issues, So if you have multiple things that you want to attack, LDA might be a little more helpful. So that's like backtracking back to LDA. The thing is, LDA doesn't really use word embeddings, but I think it does a pretty good job at retaining context because it allows for each row to be assigned to different clusters. But the thing is, it doesn't really take into consideration the meaning of words. And I think I'm going to send this out again. I'm going to write like a little summary for each resource I send out. What was I going to say? Yeah, you still end up having to assign the topics manually. So there's not going to be a model out there that's going to tell you like, okay, these are your best clusters. So there's that. So I talked about clustering and then word embeddings. Last thing I want to talk about is predictive text. I don't know if any of you guys are interested in predictive text, but it is something that's interesting, in my opinion. I've had like a couple students do projects using predictive text, and it's been something that like they implement like as a fun thing to show people at the very end. So let me see if I can let me pull up one of them that was pretty cool. I'll pull up one that was like really intense, and then one that's like a little more doable. So here, let me just open these up real quick. There's this one and there's this one. So this is one that one of my past students used a recurrent neural network to basically write a book. He trained this RNN on, I think, the Gutenberg library, Project Gutenberg, of like all of those free ebooks. And he trained it on a character by character basis. So basically, like if you see a letter A, what's the probability that like the next letter would be what? And he created a whole book after this. This is very, very intense. Like each training took like about 20 hours. So I wouldn't recommend doing this, but it was pretty cool. This is like a simulation. You would start by like doing some, inputting some text to start, and then they would just automatically complete. And this is done with an RNN. I'll send this out because I think it's just fun to look at and to see like, these are really things that like you can still build with a lot more time and like if you're really invested in neural networks. But yeah, this student did this. Yeah, and I think you can see he does go into a bit of explanation in this README that like because it was trained on such old books, a lot of like the tone of what was being output was like very like I don't know, like of the like not this century. That was a cool one. Another one that was more that I think is more attainable. Doesn't use RNNs, but uses Monte Carlo methods. And Monte Carlo methods is just like a probability method. So this person, he just started his project by just building a text classifier built on Yelp data. So to just see like if he could classify whether a Yelp review would be 1, 2, 3, 4, or 5 stars. So start off as a very simple classification project. He did like everything and he got done a little bit early. So he wanted to try this out and he did. And so he tried neural networks, but that just took a very long time. And then he does go into explanation as well. So I'll send this repo out because I think it's an interesting read too. But you use a Markov chain where you basically train a model to like look ahead. It's kind of similar because you look at probability. So let's say like you have the word the. You look in like every time that the word the happens, what is the word that comes right after that? And then based on those like probabilities, like how often does like the end, how often is the next word end? And then based on those probabilities, you generate this. And apparently it was pretty effective. I'm going to admit that I've never built my own text generator, but I just think they're really cool projects. And these are like really nicely commented notebooks that if you wanted to like see how they did it, I think it's just cool to see that it's doable. But yeah, the neural network stuff is a little intense, but I think like the Monte Carlo methods are actually pretty effective. So that's pretty much all I wanted to talk about. Are there any questions about anything? Awesome. I'm gonna like put together a bunch of resources. I think deep NLP is extremely interesting. I might get these resources out, if not tonight, tomorrow, because I just want to like have a little blurb as to like what each thing is. So I'll take some time putting that together. But yeah, that is all I have for you guys. Oh, is there something in the chat? Oh, Andy, you had a question for me like 10 minutes ago. Is that like when you add, you mean like when you add clusters? I forgot what I was talking about during this time.
We're talking about the word embeddings and adding them together. My question was where you would add that to your model in terms of like the actual lines of code. Where would you take that sum and plug it into your model?
Yeah. Okay. So in my case, each sum is each row. Because let me just reshare my screen again and show you the project more specifically. So let's see, not this one. Yeah, wait, this one. This one's right. Scroll down. So it started as this. So these were all my searches, the search terms that I had. And what I wanted to do is to convert each of these like phrases into vectors. And so each of these words started off as a vector, and then I added them together to just represent like the entire search, if that makes sense. So that's why each row is actually the sum. Yeah, I'll send out some like starter code for this.
Right, and that's where I got lost, is how you would actually embed that into, or how you convert your row into that vector for that specific row.
Yeah. I used the Lambda function. I know I was actually looking for my own code here, but I think I must have deleted it because I ended up just like reading a CSV that has it nicely vectorized. But yeah, this is what it ends up looking. This is what you end up throwing into the model. I kept this just for a reference, but yeah, literally you're just like feeding in like a bunch of numbers to your model, and basically this first row of numbers of 300 numbers represents PDX gas. Yeah.
And because they're all 300, they all map to the same length. And so the vectors are all the same. Got it.
Mm-hmm. Yeah. So this is actually really useful if you have like, yeah, different lengths. It doesn't really matter if you have words that are outside of your training data. So let's say in your like unseen data, you have words that you didn't have in your training set. I think that was an issue for like, I think those of you who did NLP in your last project, if you had like a word that was unseen, you would just not consider it at all. So there's that. Yeah. Cool. We are about right at time. Any last questions? All right. In that case, have a good night, you guys. As usual, I'm always on Slack. So, bye.